So today we're looking at Chapter 5, Section 3, which is solving multi-step inequalities. And one of the first things we want to look at is a type of word problem that you see in multi-step inequalities, and that's a commission problem. So a salesperson may make a monthly salary and earn a commission on each of her sales. To find the number of sales she needs to make to pay her monthly bills, you can use a multi-step inequality. So some things for us to think about. So what information is needed to solve the inequality for the number of sales, and which inequality symbol, either greater than or equal to, should be used to represent the situation. Pause the video. Please take a moment to think about this. Okay. So really what we're really talking about is this. Anytime you get a commission, you have a base salary, and that's your salary, and then for all the sales that you make a percentage of those sales. So if you make $100 worth of sales, you get whatever the percentage you and your boss, your employer have agreed upon. And if you want to pay your bills, that has to be greater than or equal to the income that you needed. So what information is needed to solve this? Well, these are really the three pieces of information. The base salary, the commission to be paid on each sale, and the income needed to pay the monthly bills. And also, we want to look at which inequality symbol, greater than or equal to, should be used to represent this situation. Well, if we really look at this, since you need to pay your bills, you need something that's either equal to your bills or more than your bills. It wouldn't make sense to have anything that's less than your bills. So the amount the salesperson needs to earn from the base salary and on commissions must be at least, which means greater than or equal to, the income needed to pay the bills. So the first thing we're going to look at is a real-world problem. We're going to look at a problem that I would actually talk to my physics kids about. But what we're going to do is first look at one of the astronauts from Apollo 12, I believe it is, on the moon, the American flag in the background, very patriotic. So let's read through the problem and see if we can figure it out. So the gravitational force on the moon is 0.17 times the force on Earth. So a 10-pound object on Earth will weigh 0.17 times 10. It's not going to weigh the actual 10 pounds that it would weigh on Earth. It should weigh less than that. And in this case, it would weigh 1.7 pounds on the moon. If an astronaut weighs 165 pounds and is carrying a pack, his weight including the pack cannot exceed 34 pounds on the moon. This is a real-life type of problem. Sometimes you have to, well, not sometimes. If you're going to the moon, you need to blast off and get there, and you need to carry everything that you're going with you. So what is the maximum weight of the pack on Earth? So let's look at that. So this is really what we're talking about originally. If we just think about what we're talking about, there's a maximum weight that we have to have on the moon. The weight that we bring to the moon in moon weight has to be less than that. And we're talking about 34 pounds on the moon. If we're looking at the Earth weight, well, the Earth weight is really the astronaut's Earth weight plus the pack. And the pack is something we don't know, so we want to give that a variable. But we do know that we have to multiply anything that's on Earth by this 0.17, just as we did here. Okay? So this 10 pounds over here actually weighed less on the moon, so we have to use that conversion to actually get the weight to what it would actually be on the moon, while keeping in mind it has to be less than or equal to 34 pounds. So let's keep looking. So the first thing we're going to do is we're going to substitute in the actual math language for the English. All right? 0.17 is the conversion. 165 pounds, is the weight, Earth weight of the astronaut. X is the pack, because we don't know how much that is. And it still has to be less than or equal to 34 pounds, which would be how much it would have to be on the moon. Okay, we're going to use the distributive property first, and then after we distribute, we get the next line. After we get the next line after that, we need to get the variable by itself, and it makes the most sense to move the thing that's on the variable side next to the variable that's not attached to the variable. And again, we're moving the thing that's positive, it's additive in versus negative, we're moving it to the other side. When we do that, we end up with something times the variable is less than or equal to 595, or 5.95. And so since this 0.17 is attached to the x by multiplication, we do division to get rid of it. We're dividing by a positive, so there's no need to flip our inequality sign, and we end up with x must be less than 35 pounds. So what that's telling you is, and this is how we have to kind of finish out the problem, what is it telling you? It's telling you the pack can be up to and equal to 35 pounds on Earth. Because when we get to the moon, it's going to be less, and using our conversion factor, that will put us below or equal to the 34-pound weight limit. So now we're going to look at a problem where you actually have to just solve it. It's no word problems involved. It's not words involved in it. So it's saying solve minus 2t is greater than or equal to minus 6. And you also have to graph your solution. All right? So the first thing we're going to look at is we're going to look at the original inequality, make sure we understand what we're starting with first. Now, since this inequality has a minus 8 and it has a minus 2 that's actually attached to the t, we want to move things away from the t, leave the t where it is. The additive inverse of that is adding 8. So we're going to add 8 to both sides. That cancels the 8 on the left. And then you have a minus 6 plus 8, which is positive 2. Now you have negative 2t is greater than or equal to just a 2. And so because the negative 2 is attached to the t by multiplication, we need to divide. We're going to divide both sides by a negative number. And because we're dividing both sides by a negative number, we need to change the direction of our inequality symbol. And that's what it's saying on this side. When we do that, we remember from previous lessons that that actually preserves the truth statement that we have here. Preserves the fact that when I divide by a negative or multiply by a negative, I have to flip this inequality symbol. Okay? What we end up with is t is less than or equal to negative 1, because we had to flip our inequality sign, and we're going to write that in set builder notation, which looks like the solution set, which means the answers, and set means group, so we're really talking about the group of answers. Okay, and this is what it is. It's the variable that we use, t, such that t is less than or equal to negative 1. Now, in order for us to graph our solution, we want to remember how we graph. We take basically what I call the boundary number, and we want to put that on the graph somewhere in the middle. That would be negative 1 for us. Then we want to read our inequality statement, so it's saying that t is less than or equal to negative 1. So less than or equal to, the or equal to gets the closed circle, because we're talking about t being less than numbers go to the left, so I draw my arrow to the left. I've completed graphing this problem. So now what we're really looking at is the next type of problem. And so what we want to do is we want to kind of decipher what these words are telling us. Okay? So we're going to define a variable. We have to write the inequality that goes with it. So we're given it in words, and we need to write it in math language. Then we have to solve our problem. And then we want to check. Okay? Even if it's just kind of an anecdotal check or an informal check. So what's being told to us? 16 minus 3/5 of a number is at most 2/5 of the number minus 12. So in both places we're talking about the number, so it's the same number, so we only have one variable that we're dealing with. We're going to write our let statement to define our variable, saying let n be the number. So we know what we're talking about. You don't have to write it up there. You have more room on your paper. Okay? And so now we need to start translating. So they tell us that it's 16 minus, okay, 3/5. 3/5 is a fraction. Of a number means we're going to multiply. So it's 3/5 n. Is at most. So we hate to remember these statements. So is our statement that allows us to know that this is a inequality symbol that we're going to have to use here. And at most tells us the thing we're talking about has to be less than or equal to, because at most is a ceiling or a maximum, less than or equal to 2/5 of a number, of the number, so we're talking about the same number, so we're using n again, minus 12. Okay? And so what we're going to look at is these words that we just did. We're going to basically take them out and put them like this. And so again, we recognize that at most is a ceiling, so the thing that we were talking about, this whole side, is at most, which means less than or equal to the other side. Okay? is at most the other side. Okay? So if it's at most 50, 50 would be on this side, but it's not telling you that. It's just an example. So now what we're going to do is we're actually going to solve this. Okay? And so in order to solve this, there are a number of ways we can do it. I'm going to use the way that we are a little more comfortable with. And so we have 16 minus 3/5 n is less than or equal to 2/5 n minus 12. In these cases, we can either get our variables to one side, but I like to clear our fraction first. So I'm going to multiply everything on both sides, which is very important to remember. Everything on both sides by our common denominator. Okay, it can't just be one thing. It's everything in those parentheses on both sides must be multiplied by this 5. So 5 times 16 is going to give us 80 minus 15 over 5. I know that you can reduce that, but I'm just doing it out so you see what's going on. Is less than or equal to 10 divided by 5, because 2 times 5 gives you this 10 over here. And minus 12 times 5 is 60. And so now what I want to do is recognize that when I multiply by the least common denominator on both sides, what it does is clear my denominator. And how does that happen? I have 80 now minus 15 divided by 5 is 3n. Notice you end up with the same numerator if you pick the proper, if you pick the same thing for your denominator as you have for your least common denominator. Is less than or equal to 10 divided by 5 is 2n minus 60. Now it doesn't change your answer. Please remember it doesn't change your answer. That's very important. All it does is put it in a different form so that you can actually solve it maybe a little bit easier without moving around the fractions. So now I'm going to get all of my variables to one side, move all of my numbers to the other. So I'm actually going to move this so that I keep my variable positive. Again, you could do it a different way. I'm moving the 3n, and when I say move, I'm adding the additive inverse to make 0. And then since I'm moving my n's to the left, I'm going to move my other number, this would be the 60, to the right using the additive inverse again. So when I do all of that, this cancels and this cancels to make 0. I have 80 plus 60 is 140, which is less than or equal to 5n. What I'm going to do then is I'm going to divide by 5n because I want to get n by itself. And then what I'm going to end up with is 28 on one side and n on the other. Now that I have 28 is less than n, I write that in set builder notation. So n such that, and I'm actually going to flip this around so n comes first. Again, just remembering that if n is on the open side where the alligator likes to eat, that even when I flip it around, it has to be on that side. So we're going to have n is greater than or equal to, 28. Close my fancy brackets, and that would be set builder notation for this answer. Okay? So really, you can kind of do an informal check on this one, okay, by going through your steps and making sure that you've done it correctly. They're not asking you to define what your variable is, so you should be okay from there. On this problem, we're going to look at using the distributive property to solve an inequality. And so what we're going to do is just use what they give us and go from there. We're also going to end up graphing this problem at the very end. Okay, notice there's only one inequality symbol, so there's only one thing that we're going to end up having to do. So when I do the distributive property, I must distribute the thing on the outside with everything on the inside, so that's a positive 2. So positive 2 times p is 2p. Positive 2 times minus 3 is minus 6. Minus 3 times positive 2p is minus 6p. And minus 3 times positive 6 is minus 18. Notice there's no distributive property on the right side, so I'm going to end up with 4p again. Okay? I'm going to combine all my like terms, and then I'm going to move all my variables to move my variable to one side, move the things that are not my variable to the other, and I should be able to finish. So what I'm going to end up with is 2p minus 6p because they are like terms, and I'm going to get up with minus 4p. I'm going to end up with a minus 6 and a minus 18, which is going to give me a minus 24 because they are like terms and both have minuses. So we're going to put them together. It's greater than 4p. Again, I'm going to move things that I need from one side to the next. So what I'm going to do is, since I have things with p on the left and just p's on the right, I'm going to move my p's to the right. Again, I'm doing the additive inverse first. Okay, so I get minus 24 is greater than, well, I have a positive 4p and another positive 4p, which gives me 8p. I'm not completely finished. Please recognize that even though I'm dividing by 8 on both sides, 8 is a positive number, so even though the negative 24 is negative, I'm not flipping my inequality sign. So I get minus 3 is greater than p. Okay, and set builder notation, I'm going to have p is my variable such that p is less than minus 3. Okay, some of you like to switch it around when you graph, so it kind of reminds you of which way the arrow can go. That's fine, but I like to do it so that I just show that I know the math that's going on and recognize that I have my number, which is minus 3, since I have just greater than or just less than, depending on which way you're reading it. I'm going to have an open circle. Now I'm going to look over here, and I'm going to recognize that just an open circle goes on my boundary number, which is minus 3. P is less than that minus 3, and since P is less than that minus 3, less than numbers go to the left, and there we go is my arrow. The next one we're going to look at has to do with empty sets and all real numbers. That's kind of a clue that we're going to end up with something that's a little bit trickier than we might have had before. I'm going to make this a little bit bigger. Okay, and we're not graphing this one, but it's a good idea just to keep in mind what's happening. So I clearly have the distributive property here on both sides, so I'm going to do that first. So I end up with 2 times x and 2 times 3, which gives me 2x plus 6, which is less than or equal to. I'm going to do the same thing with this entire 1/2. Okay, it's your prerogative. If you wanted to multiply everything by 2, you'd have to multiply everything by 2. I'm going to distribute the 1/2 because I have even numbers on the inside, so if I divide them by 2, I should be okay. So I have 1/2 times 4, which gives me 2. Just a little sidebar. 1/2 times a whole number 4. I put a 1 underneath and I multiply straight across. So I get 4 over 2, which gives me the 2 that I just said. 2 times 1/2 is going to give me positive 1 because they're both positive. And the minus 1 is still on the outside. It wasn't touched by anything. What I'm going to do now is combine all my like terms. So I get 2x plus 6 is less than or equal to 2x by itself because these two cancel. And what I'm going to do is try to move all of my variables to one side. Since I have a 2x and a 6 on the left, and I just have a 2x on the right, I'm moving all of my things to the right. Sometimes you'd move them to the left. It just depends on where you have less things. I'm going to minus 2x from both sides because I'm doing the additive inverse, and I get 6 is less than or equal to 0. Now, when looking at this problem, 6 is less than or equal to 0. This is clearly not true. 6 is never equal to 0. 6 is never less than 0. And so this is clearly always a false answer. Okay? Because we don't have any more variables, we haven't solved to get an actual answer where we see x is equal to or x is less than or x is greater than an actual number. Since that variable is missing, and if we did it correctly, that tells us specifically that we have one of the special cases where it's either always false, which means no matter what numbers I plug in for the variable in the very beginning of the problem, I always get a false answer. It is impossible to get a true answer. And if it's impossible to get a true answer, this never has a solution, so we call it no solution. Now, no solution can also be written like this, which is represented by what's called an empty set. And it's called an empty set is because we're looking for the solution set. We're looking for the group of answers. Well, if there aren't any group of answers because there's no solution, then that set, that group, is empty. So we call it an empty set, which means no solution. The next thing we're going to look at is another problem just like this, and probably if you have figured this out, if we're doing empty sets and all real numbers, we're going to look at the empty set first, and now we're going to look at the all real numbers. But we don't know that until the very end of the problem, so it's very important that we solve correctly, go over each one of our steps, understand where our steps take us, and how we got from the beginning of the problem to the end by using proper mathematical logic. So again, I see distributive property. I'm going to do that. Okay, I like to draw arrows to remind myself of what's happening. So I do 12 times t, which gives me 12t. I do 12 times 4, which gives me 48. I have minus 3t on the left side, which is greater than 9 times t, which is 9t, plus 36. I'm going to combine my like terms, and as I can see, I have a minus 3t and a positive 12t, which gives me a 9t plus 48, because nothing was done to the 48, which is greater than 9t plus 36. Now you can kind of already see that if I have the same thing on both sides, I can technically cancel the same thing on both sides, and I'm going to end up with 48 is greater than 36, if you can kind of look ahead and see where we're going. If you can't see that, that's okay. What we're going to do is actually finish the problem. So it doesn't matter which way we're going. Both of the variables have the same coefficient. So I'm going to do the additive inverse on both sides. And please remember that when I do the additive inverse, I get 0. So that's 0 plus 36, and that's 0 plus 48. Now I know that you can cancel to get 48 is greater than 36, but please remember when you do the additive inverse, you're canceling to get 0. What you're actually doing is you have 48 is greater than 36. This is always true. 48 is never not greater than 36. It's never equal to 36. Since there's no variable to vary, then it will never change. So what we're now going to do is say, hey, if an empty set means it's always false, it's no solution when it's always false, because I can plug in any number when it's always false and never get an answer. If something that's always true is what I have, if I plug in any number into the variable in the beginning of the problem and solve it out, I will always get 48 or always get something that's true. Always. It can't change because there aren't any variables left. And so what we say for this is we're going to say all real numbers. And what that says, well, real numbers. What that says is that all real numbers can be the solution of this. Okay? The solution to this problem is all real numbers. Any real number I can think of, I can plug into that variable, and that gives me the answer. So this is my solution set, otherwise known as my group of answers. Thank you, and I'll see you guys tomorrow.